Welcome everyone. I'm excited to have you here today. In this presentation, we'll be exploring the Rockwell Hardness Test, focusing on methods A, B, and C. We'll cover how the test works, the different scales used, and its practical applications. So let's dive in and discover the essentials of this important testing method. Let's take a closer look at the test standards. The key idea here is that our testing process is standardized, meaning it follows specific guidelines to ensure that results are consistent and reliable, no matter which laboratory conducts the test. This consistency is crucial because it allows us to compare results accurately across different settings. Now, there are several important standards to keep in mind. First, we have the Indian standard, IS 1586, which provides the local guidelines for testing. Then, there's the ASTM standard, ASTM E18, which is widely recognized internationally, especially in North America. And finally, the ISO standard, ISO 6508, offers a global framework for hardness testing. All these standards specify critical details like the loads to be applied during testing, the type of indenter used, and the dwell time, the amount of time the load is applied. They also outline how to verify that the testing equipment is functioning correctly and how to report the results accurately. Connecting this to the overall theme, understanding these standards ensures that our testing methods are not just consistent, but also credible and comparable worldwide. This uniformity is essential for quality control and for maintaining trust in the test results we rely on. So, what is hardness exactly? Well, it's essentially a material's ability to resist being permanently indented or scratched when a load is applied. Think of it as how tough or resistant a material is under pressure. In industries, measuring hardness quickly can tell us a lot about whether the heat treatment process was successful. It's a rapid way to assess if the material has the desired properties after processing. One of the most common methods we use is the Rockwell test. It's popular because it provides a direct reading, no need for complex measurements or calculations. This makes it especially useful for routine inspections and quality control in production environments. So, by checking hardness, we can ensure that parts meet the necessary standards efficiently and reliably. Let's take a closer look at the principle behind the Rockwell Hardness Test. First, a small preliminary minor load of 10 kgf is applied. This initial step helps to establish a consistent reference position, ensuring that all measurements start from a standardized baseline. Next, a major load. Depending on the test scale, it can be 60, 100, or even 150 kgf is applied on top of that minor load. This larger load causes the indenter to penetrate deeper into the material, creating a visible indentation. Once the major load is removed, we measure the permanent depth of this indentation automatically. The machine then converts this depth directly into a hardness number, giving us a precise measurement of the material's resistance to deformation. This process is fundamental because it provides a standardized way to evaluate the hardness of different materials, which is essential for assessing their suitability for various applications. Let's take a moment to understand how the Rockwell method differs from Brinell and Vickers. Both Brinell and Vickers testing require the use of a microscope to measure the size of the indentation. This means that the operator needs to carefully observe and measure the indentation under magnification. This process can be quite dependent on the skill of the operator, which introduces variability, and it also takes more time to perform. Now, in contrast, the Rockwell test simplifies this process significantly. Instead of optical measurement, it evaluates hardness based on the depth of penetration of the indenter. This approach eliminates the need for optical measurement, making the process much faster and easier. It's especially well suited for shop floor environments where speed and simplicity are key. So, overall, Rockwell offers a more efficient, straightforward method that can be easily integrated into production workflows. All right, let's take a closer look at the different types of indenters used for hardness testing. Here, we see that for HRA and HRC scales, we use a diamond cone as the indenter. This shape allows us to get precise measurements on harder materials. On the other hand, for HRB, we use a 1/16-inch ball indenter, which is better suited for softer materials. The key point here is that the selection of the indenter depends on the material's hardness. Choosing the right indenter is crucial because it directly impacts the accuracy of your hardness readings. Proper selection of the scale and indenter ensures that the values you obtain are both accurate and meaningful. So, when you're conducting a hardness test, remember to match the indenter type to the material you're testing. This helps you get reliable results that truly reflect the material's properties. Before we begin testing, it's crucial to always verify the machine's accuracy using standard test blocks. This helps ensure that our readings are reliable and precise. Now, let's go through the testing procedure step by step. First, we prepare and clean the surface of the specimen to remove any dirt or debris that could affect the measurement. Next, we set the desired indenter according to the specific scale we're using, whether it's A, B, or C, since each has its own requirements. After that, we carefully place the specimen onto the testing platform, making sure it's properly aligned. Then, we apply a minor load, typically around 10 kilogram force, to seat the indenter and stabilize the setup. Following that, we apply the major load, which varies depending on whether we're working with scale A, B, or C. This load is essential for creating the indentation. Once the major load has been applied for the required duration, we carefully remove it. Finally, we read the hardness directly from the scale or indicator. This straightforward process ensures consistent and accurate hardness measurements, which are vital for assessing material properties in our overall quality control. Let's take a moment to watch this video to really understand the concept we're discussing. As you watch, pay attention to the key points and how they illustrate the ideas we've been exploring. This visual will help clarify how these concepts come to life in real-world scenarios. Remember, the goal here is to see the practical application and the impact of these strategies. Once the video finishes, we'll connect what we've seen back to the overall theme of the presentation and discuss how it reinforces the key messages we've been working on. So, let's go ahead and watch.
We are going to check the HRC test block, so first confirm that the diamond indenter is installed. Now set the load to 150 kilograms force as required for the HRC scale. Place the test block properly on the anvil. Rotate the anvil and tighten it until the minor load is applied. The small needle reaching the red mark indicates the 10 kilograms force minor load. Now the major load of 150 kilograms force is applied automatically. Wait for the dwell time of about 3 to 5 seconds, until the large needle stops moving. Now release the major load and observe the position of the large needle on the outer scale, which is for HRC. The reading is 26 HRC. We can see the value of test block is at 25.4 HRC, plus minus 1 is acceptable.
When it comes to precautions, the first thing I want to emphasize is that the surface we're working with should always be clean, smooth, and completely free from any scale or contamination. This helps ensure accurate results and prevents any interference during testing. Next, when we're preparing indentations, they need to be positioned away from the edges and from each other. This spacing is crucial because it minimizes the risk of the indentations affecting each other or being influenced by the edges of the specimen, which could skew our measurements. Another important point is the specimen thickness. It should be sufficient to prevent the support from influencing the test results. If the specimen is too thin, the support can distort the measurements, so always check that the thickness is appropriate. And finally, before we start any testing, always confirm that the scale is correct. Verifying this ensures that all our measurements are accurate and that we're interpreting the data properly. Paying attention to these precautions helps us maintain the integrity of our testing process and ensures reliable, consistent results. Let's take a look at the advantages and limitations of this particular method. First, on the advantages side, it's extremely fast, allowing for quick assessments without much delay. It also provides a direct reading, meaning we get immediate results without complex processing. The process involves minimal operator influence, which helps ensure consistency and reduces the chance of human error. Because of these features, it's especially ideal for production work where speed and efficiency are crucial. Now, moving on to the requirements, you'll be pleased to know that this method requires no microscope, which simplifies the setup and makes it more accessible. Additionally, it produces small indentations, which means it's less invasive and more suitable for certain applications. However, like any technique, it has its limitations. It's not suitable for very thin materials, as the process could damage or deform them. Also, rough cast surfaces can pose challenges, likely because the surface irregularities can interfere with the accuracy or reliability of the readings. Overall, this method is a great tool for rapid, straightforward assessments in many production environments, but it's important to be aware of its constraints to ensure it's applied correctly. When reporting hardness, it's essential to always include the scale designation along with the number. For example, instead of just saying 60, I should say 60 HRC. This clarity ensures everyone understands exactly which hardness scale has been used. It's also important to follow established standards when reporting these results. The main guidelines come from organizations like IS, ASTM, or ISO. Adhering to these ensures consistency and accuracy across different reports and laboratories. So remember, always specify the scale and follow the relevant standard to make your reporting clear and professional. This attention to detail helps maintain the integrity of your data and supports reliable comparisons. Let's keep in mind a few things from our experience. First, when you're checking for HRC, if the value is below 10 HRC or above 65 HRC, there's a good chance of error. So, it's always a good idea to verify that sample at HRA or HRB to ensure accuracy. Secondly, if you're checking for HRB and the value falls below 10 HRB or exceeds 90 HRB, again, there's a possibility of measurement error. In this case, it's best to check that sample at HRA or HRC to double-check your results. Finally, a quick note on terminology. These days, HRB is often referred to as HRBW. That's because in recent times, a tungsten carbide ball indenter is being used instead of a hardened steel ball indenter. This change helps improve the precision and reliability of the measurement. So, always remember these key points to maintain accuracy in your hardness testing. Let's take a moment to look at this comparison chart for the different Rockwell hardness scales, HRA, HRB, and HRC. Each of these scales uses different indenters, loads, and is suited for testing specific types of materials. Starting with HRA, which uses a diamond cone, also known as a braille, and a load of 60 kilograms force. This scale is typically used for very hard materials, like carbides or thin hardened layers. It's ideal when you need to measure the hardness of materials that are extremely resistant. Next, we have HRB, which employs a 1/16-inch diameter steel ball as the indenter, with a load of 100 kilograms force. This scale is more suited for softer metals such as brass, aluminum, and low-carbon steels. It provides a good measure for materials with moderate hardness. Finally, HRC uses the same diamond cone indenter as HRA, but applies a higher load of 150 kilograms force. This scale is primarily used for hardened steels, tools, dies, and machine parts, materials that require a more precise hardness measurement at the high end of the scale. In summary, these three scales are tailored to different material types and hardness ranges. Understanding which scale to use helps ensure accurate, reliable testing, and ultimately supports quality control across various manufacturing processes. This comparison underscores how the Rockwell test adapts to different applications, reinforcing its importance in material analysis.